Hi everyone, I'm Wei-Ting Xu. I'm a postdoctoral researcher of heat transfer laboratory at Yonsei University. I just got my PhD degree this year and my advisor is Professor Hyung-Hee Zhou. Before I start the presentation, I want to convey my gratitude to my advisor and all the committee members who helped me to improve my thesis quality. As you can see from this slide, I'm gonna give a talk about how micro and nanostructural substances affect heat transfer characteristics under boiling conditions. Basically, my presentation can be divided into 5 categories as shown on this slide. First, I'm going to introduce some basic knowledge about boiling heat transfer and the objectives of this study. There are 3 goals of boiling heat transfer that researchers want to achieve: to promote onset of nucleation boiling, which means the starting point of phase change; to improve heat transfer coefficient, which means the increase in heat dissipation capacity; and enhance critical heat flux. The critical heat flux here can be seen as a critical point of heating systems. When heating system reach this point, the entire heating surface will cover by a vapor film that blocks any further heat transfer from the surface to the water. In general, surface modification considering with surface wettability, capillary leaking, and surface roughness is widely used to enhance overall heat transfer performance of heated surfaces. These parameters are significantly dominated by the surface morphology of structural surfaces and can be manipulated using chemical deposition, MEMS, and microcontact printing methods. Here, hence the research objective of my PhD thesis and to provide a design guideline of multi-scale structural subsets for boiling heat transfer enhancement to overcome the thermal management issues of high power applications, especially for the data server cooling using immersion cooling technology as shown in this video. Now I'm going to talk about the experimental facility in our laboratory. Here are the schematic diagram of experimental setup that I used to conduct heat transfer experiments under pool and flow boiling conditions. As you can see from this slide, the experimental facilities, including the test station and the gaseous temperature detector sensor, were designed and constructed by myself. And here, the RTD sensor has high accuracy and high response time for temperature measurement, which can be fabricated on the backside of micro or nanostructural surfaces. Now I'd like to talk about the first content of my PhD thesis. The research objective of the first content aimed to experimentally determine the influence of heterogeneous wettability pattern surfaces in terms of the pattern configuration on heat transfer in flow boiling. Herein, the pattern configuration will circle, triangle, and inverted triangle patterns spaced at 0.75 millimeter and 1 millimeter along the flow direction, respectively. I created surface composed of hydrophilic substrates and hydrophobic pattern arrays following this fabrication procedure based on MEMS method, including a standard photolithography, developing and lift-off process. In addition, to confirm whether the tested subsets were successfully fabricated, I conducted a droplet test on the structural surfaces as shown on the figure on the right. When a droplet is deposited on the tested surface, a liquid film will only cover on the hydrophilic substrate, while the hydrophobic pattern region remains dry. According to the experimental results, only wettability pattern surfaces reveal a higher critical heat flux compared to the silicone substrates at 40 to 43%. And among the wettability pattern surfaces, the critical heat flux did not show a strong dependency on the geometry of hydrophobic pattern arrays. If you look at the graph regarding the bubble characteristics of tested surfaces, we can find that the surface consists of hydrophilic substrate and hydrophobic pattern arrays reveal several liquid passes compared to silicone substrate, which was covered by a vapor film when the heat flux was at 80 and 170 watts per centimeter squared. And this observation indicates that the wettability pattern surfaces can ensure more coolant supply and thus efficiently prevent a premature dry out and a sudden transition of critical heat flux. In addition, this underlying mechanism of heat transfer enhancement of these structural surfaces can be theoretically determined by analyzing bubble lifter forces in a horizontal flow channel. Please have a look at the graph on the right. If the surface tension force in the x direction is lower than the shear lift force of working fluid. Then the vapor bubble will start sliding on the surface. On the other hand, the vapor bubble will depart from the heating surface once the surface tension force in the y direction is lower than the buoyancy force that forces bubble to rise. And according to the relationship between the surface tension force and the bubble detachment behavior, the bubble lift force on various hydrophobic pattern shapes can be seen as a ratio of surface tension force in the y direction to loss in x direction. This mathematical results show a close agreement with the experimental results, and we found that the surface with triangle hydrophobic pattern arrays with interspacing of 1 millimeter was the optimal design among the tested surfaces. Now I'm going to talk about the second content of my PhD thesis. Here I created surface composed of micro tidy pillar arrays that generate a unidirectional weakening behavior to enhance it avoid heat transfer. And as you can see from this video, the vertical pillar will uniformly tidy in the same direction. The tidy pillar substrate will generate unidirectional weakening, and in terms of stick jump phenomena, and that drives spark liquid to propagate along the pillar tidy direction. And therefore, these structured surfaces are expected to enhance the heat transfer by generating the unidirectional weakening to augment the capillary driven force when the liquid propagation corresponds with pillar tidy direction. And please look at the graph on the right. I fabricated the vertical pillar arrays using PDMS materials on bar silicon substrates based on replica molding method. Subsequently, the vertical pillar surfaces were laid on a quartz plate in a sputter coater with a fixed angle of 45 degrees. And one side of each pillar was coated with a 200 nanometer gold layer with a fixed depositing rate of 0.27 nanometer per second. So we can create a surface composed of silicon substrate and vertical polymerized pillar arrays and tidy pillar arrays as shown on this slide. To determine the surface morphology effect of the tidy pillar substrates on weakening characteristics, I conducted a weakening measurement on tested surfaces based on a vertical weakening test method. This measure approachment has been widely used to evaluate the capillary action governed by structural surfaces. And as you can see from these videos, when pillar tidy direction towards the direction of liquid propagation, the bulk water passes to half of the tested surface with a pillar spacing of 250 micrometer. In contrast, the liquid propagation was seen when weakening was against the direction of pillar tidy. According to this Washburn's equation, the weakening characteristics can be determined by measuring the position of weakening length of true square root of time. The weakening velocity increased here in as you can see from this figure, we can find that the weakening velocity increased when the pillar will tidy towards the direction of liquid propagation composed compared to those surfaces against the flow direction of the direction by 32 and 64% for surfaces with spacing of 250 micrometer and 500 micrometer. Regarding the boiling heat transfer characteristics of tested surfaces, the surfaces having tidy pillar arrays spaced at 250 micrometer reveal the hydrous overall heat transfer performance among the tested surfaces. On the other hand, the critical heat flux of the tested surfaces composed of pillar arrays was significantly enhanced when polymerized pillar tidy toward flow direction, showing a strong flow dependency on pillar tidy. Now I'm going to talk about the last part of my PhD thesis. In this part, I created zinc oxide nanowires with various nanowire lengths on bar silicon substrates and determine the surface morphology effect of nanostructured surfaces on heat transfer in pool boiling. Here are the same images regarding tested surfaces, including a bar silicon substrate and surfaces composed of zinc oxide nanowires with varying the nanowire length from 2.6 to 12 micrometer respectively. The weakening characteristics of structural surfaces can be determined using the Washburn's equation as previously mentioned, as previously discussed. Here, by measuring the position of weakening length to the square root of time, we can determine the weakening characteristics of this tensor surface. Here, overall, the critical heat zinc oxide nanowires reveal a remarkable weakening characteristic when compared to silicon nanowires fabricated using chemical etching method. Here, the capillary driving force of zinc oxide nanowires significantly augmented when the nanowire length grew above 5 micrometer, indicating that the surface composed of zinc oxide nanowires with higher nanowire length could efficiently ensure the surface current supply and last extended boiling crisis. And compared to the surface composed of silicon nanowires, the zinc oxide nanowire substrate show a higher significant enhancement in critical heat flux by 85 to 195% shown on this slide. And now I'll summarize our findings based on my PhD thesis. Firstly, I created surface composed of true wettability construct regions to investigate the effects of the surface wettability and pattern configuration on heat transfer under flow boiling conditions. I also proposed a theoretical model considering with Barber-Newton forces of various pattern shapes to determine the underlying mechanism of heat transfer enhancement of tensor surfaces along the flow direction. Secondly, I used PDMS material to create a tidy pillar arrays on silicon substrate based on replica molding method. The overall heat transfer of the pillar substrates reveal a significant directional dependency of pillar tidy under flow boiling conditions. And finally, I also determined the surface morphology effect of nano-weakening structures. I fabricated zinc oxide nanowires on various substrates, including bar silicon, copper, and aluminum substrates based on micro-contact printing coupled with hydrothermal growth method. The zinc oxide nanowires have a remarkable industrial applicability than the silicon nanowires owing to its outstanding heat transfer performance, possibility of large area fabrication, and high substrate selectivity. That's all for my presentation. Thank you for your attention. If you have any questions, please feel free to contact me by sending email to this mail address, and I will try to get back to you as soon as possible. Thank you.